thank Rosario for the introduction. Thank the organizer for the invitation. It's a pleasure for me to give a lecture in this interesting meeting. It's my first time in Vienna like mathematician. And I'm going to present a joint work with Gorni, that is in the audience, and Julián Toledo, that is professor in the University of Valencia. We study perturbed one Laplacian in random world spaces. Later I give you the precise definition of random world spaces, but let me say that it's very simple. You have a measurable set, and then for each point you associate a probability, and this probability encodes the jump of a Markov process. It's simply. Okay, then we study two types of problems. The first one is we have two, for the same measurable set, you have two different random worlds, and then each of one you associate different energy functional. For instance, one of type 1 Laplacian and another of type 2 Laplacian. And then the idea is to study what is the gradient flow given by the sum of the two energies. And the second problem is in some sense similar, very different. Now you have only one random world space, and then you make a partition. The partition can be overlapping, and in each part of the partition you define an energy functional of different growth. And also we want to study what is the equation associated, what is the evolution of the differential of the energy. Okay. For instance, suppose you have set 2, and then you take in the vertical direction you take the 1 Laplacian, in the horizontal you take the P Laplacian, and then what is the evolution of the joint energy. My idea was to start what in the case of Rn, but I discovered that in a lot of lectures speak about this in Rn. My framework is not Rn, and it's happy for me to speak some of the more important mathematicians about this kind of problem are in the audience. Even in the case, there are few literature in the case 1 P Laplacian, but also it's a pleasure for me that Giga was one start with this, and also Contino Sabucci, that is one of the experts in this kind of operator in the Euclidean setting. Okay, then let me start with the random world. You have a measurable set, and you have a family for every point you have a probability. Okay, then given a distribution of mass, we define the convolution by this formula, and this describes the new distribution of the mass after one jump. Okay, and we say that a finite measure is invariant respect to the random world when we have the convolution is equal to the measure. But also we need another concept, stronger one. We define tensor product of a measure and a random world by this formula. And we say that a measure is reversible respect to the random world when this tensor product is symmetric. Okay, for instance, you have weighted graph, then the weight are symmetric. Wx1 is equal to W1. Okay. Then, for me, a random world space is the random world, and also some reversible measure. Reversible implies invariant. Okay, example. The first example is in Rn. You take the Euclidean distance, and you take a kernel J, integral equal to 1, and then you define, for every point, you define this probability, and you apply Fubini, the event measure is invariant respect to this. The second example is the weighted graph. You have a graph, you have edges and a vertex, and then we assume that the weights are symmetric, and the weight are 0 if these are not connected. Then it's trivial. You consider the degree of a vertex equal to the sum of the weight connecting with the point, then this is a probability, and it is easy to prove that this measure mu g equal to the sum of the degree is reversible and is invariant. Okay, this is another example. There are more examples. For instance, the hypergraph also can you define, associate for every point in the hypergraph, you can associate probability measure and define a random wall space. Okay. Some years ago, we started working with Solera and Toledo in this framework, PDEs. We start with the heat equation in this paper. In this paper, we study the heat equation. We study also the Shiger inequality, and we study. We start working in this for a paper of Olivier. Olivier write a paper, and is called metric random wall spaces because the space X have a distance, and then consider the Borel set like measurable set. And then define the concept of curvature. No people call, there are a lot of literature called Olivier-Ricci curvature. This curvature in graph and in this kind of, okay? And also in this paper, we see the influence of the Ricci curvature about the asymptotic behavior resolution and so on. Later, we continue working, the same author, study the P Laplacian, study the total variation flow, the Shiger problem, also the rough model, and we decided to write, with all the results, to write this. Let me do propaganda. This you have the theory, okay? But this appeared 1 year and a half, but continue working. Also, in the monograph, there is a chapter, I work with Gornick about the Lie gradient problem in this context. But we continue working, and we study different problems, in different PD problem, this problem, in this general framework. And let me say that some of the results taken here in the book even are new for graph. Even are new. Some of them are new for the non-local problem, but for graph, some of them are new. Okay, now this is the framework, and we consider the operator. The non-local gradient is, everybody knows, is given by this, and given the random wall, we define the n divergent by this formula. The n divergent of in this function of two variables I call vector field because are the equivalent to vector field in our end. We define by the formula 1/2 set y minus this. When this is symmetric, then disappear the 1/2. Okay. And we are lucky because people working in PDE without a green formula, we don't know how to prove nothing. But here we have an integration by part formula. You integrate, you take B in LP and the vector field in P prime, then this integral is equal to this double integral, and here appear the convolution. And here appear 1/2, and then appear in all the definitions. Okay, then given P greater than 1, we define this energy functional in L2. It's similar to the classical one, but here appears the 2 is due to this. We define this functional. This functional is lower semi-continuous and convex, and then the subdifferential is maximal monotone. And by the Brzezinski-Mura theorem, the evolution problem associated with the subdifferential have a unit strong solution. This is no problem. Okay. And then we define what is the MP Laplacian. The MP Laplacian is minus the subdifferential. But we need to give a minimum. You say our operator is minus the subdifferential, you don't say nothing. It's impossible to make calculation. And we prove that this operator is completely accretive. This is important in order to have estimation. If and only if that you can imagine. B is equal, the n divergent of the gradient to the power p minus 2, the gradient u, is given by this formula. Then we have a good representation of the P Laplacian. Okay. To define the one Laplacian, we need to give some sense to the BB function. we define a BB function in this framework when the integral of the gradient is finite. And the functional is 1/2 of the integral in the convolution or in the product of the gradient. A plus infinity is now a BB function. Again, we have, now here, we have also a green formula. But the green formula you need to take, like in the case, in the case of Ancelotti-Parini. You need to have the function BB, for instance, in L2, and then this you put here P, here P at P prime. But you have also an integration by part formula. Okay, and we prove a similar formula to the classical one. The total variation is equal to the supremum of the integral U divergent of vector field such that the vector field is bounded by 1. And this permits to us to prove that this functional is lower semicontinuous. Again, we have a lower semicontinuous functional, and we have convex, and then again the subdifferential is maximal monotone operator. And we define the N1 Laplacian in the same way that the P Laplacian, minus the subdifferential. But we give a characterization. The characterization is the following. I prefer the second one. A pair belongs to the subdifferential if and only if there is a function G bounded with the infinity not less or equal than 1 such that B is equal to minus this integral and D belongs to the sign. In some sense, this function G is the gradient over the modulo of the gradient when the modulo of the gradient is equal to 0. It's like in the, you remember the lecture of Gorny, when you are in Rn, you need to take a vector field in order to represent, to get a good representation when the gradient is equal to 0. Okay. Okay. Also, we consider here we need Poincaré and Sobolev inequality. We say in the case that the invariant measure is finite, we say verify this functional verifier Poincaré inequality if we have that this energy dominates the LR not that constant. And in the case that the measure is plus infinity, we say that these functionals satisfy our Sobolev inequality when you have also the same dominance. Okay, I think I have all the ingredients. Let me say that in the book we prove that the two samples, the sample of the Wittig graph and the sample of the non-log operator, verify these two inequalities. Okay. Because sometimes I need this in order to study the asymptotic behavior only. Okay. Okay, now I can start with the first problem. We have, as I say, in the same X, two random walls. We need to assume, we need to fix in what Hilbert space we define the sum of the energy, and then we need to assume that mu2 is absolutely continuous with respect to mu1, and also that the Radon-Nikodym derivative is bounded. And then in the Hilbert space that we study the energy functional is H equal to L2 of the mu1. Okay. Then we define the 1p operator. We have in the first random wall, we have the energy associated with the 1 Laplacian, and in the second, we have the energy associated with the P Laplacian. Then we know that the subdifferential of the first is equal to minus the 1 Laplacian respect to the first random wall, and the subdifferential of the second, respect to the mu2 is without this, but if you take the subdifferential respect to the Fish space, the Hilbert space H is equal to minus the Radon-Nikodym derivative times the P Laplacian. Okay. Then the idea, we want to prove that the subdifferential of the sum is equal to the sum of the subdifferential. There are general results that prove that one of the inclusion is always true, but the other you need some assumption of the energy functional, And this assumption doesn't work in our case, okay? And then, but finally we prove this. The theorem is the following. We assume the same assumption. Then, in the case that this measure is finite, or if it's infinite, you need to assume maybe for technical reason that P is greater or equal than 2. The sum of the subdifferential of the sum is the sum of the subdifferential, and then we have a good characterization of the gradient flow. It's minus 1 Laplacian in respect to 1 minus mu, the 2 Laplacian the P Laplacian respect to 2. Moreover, this operator is completely aggressive operator and have the domain. Then, if we apply, well, scale of the proof is the following. We define the operator, an operator in this product, like the sum of the minus 1 Laplacian minus mu 2 Laplacian. And the idea is to prove that this is equal to the subdifferential. Okay. First, we prove that this operator is completely aggressive operator in L2, and then, since this operator is maximal monotone, to prove the equality, we only need to prove that the subdifferential is contained in this operator because this operator is monotone. Okay? It's technical, but I don't give the detail. Okay. Then, if we apply the classical Resist-Komura theorem, we have the well-posed of the problem. This problem, for every initial data in L2, is well-posed. And also, since the operator, we prove that the sum of the two operators is completely aggressive, we have the bonus that also we have comparison principle and contraction principle. You have two solutions, then the LQ naught for every Q, even for this is important for Q equal to infinite, you have the difference of the positive part of the solution is controlled by this. Okay. What about the asymptotic behavior? The asymptotic behavior, here the winner is the 1 Laplacian. Because when P is near to 1, also you have finite extinction time, or right to the media in finite time. But here, even for P large, you have that in finite time, the solution of the problem convert to the media. We don't know the exact extinction time, but we know some bound. This in the case, this is finite, and you need to assume 2 Poincare inequality. We are in the case the measure is infinite, then you need to assume 2 Sobolev inequality, and you obtain similar result, but now you have finite extinction time. In finite time, the solution disappears. Okay. Okay. Now, the case that we take P and Q, not 1 and P and Q. In this case, the proof is similar. We need to assume here that Q is less or equal than 2, and in the infinite measure, we need to this relation between P and Q. But also we have that the subdifferential of the sum of the energy is equal to minus the N1 Q Laplacian minus mu N2 P Laplacian, and also is completely aggressive. The more difficult, not more difficult, but with different proof, we study the case that you have one Laplacian. We take the one, we want to solve formally this kind of equation. Here you have the one Laplacian respect to one of the random wall and the one Laplacian respect to the second. And we prove that the subdifferential of the sum is equal to the minus 1 Laplacian minus mu 1 Laplacian. Here the proof is totally different, and here you will use a lot the fact that this operator is homogeneous or degree 1. It's very important in the proof. Also, we have apply again Resist-Komura theorem, and you have the problem is well posed. We have comparison and contraction principle. Okay. And now the second problem. The second problem, I told you, now we fix a random wall space, and we consider you take the support of the probability mx, and you divide this in 2 parts. but maybe this can overlap. This set can overlap. Okay, then this is the energy functional. We consider integrating respect to you fix x and integrated in this part of the partition, you consider the energy of the one Laplacian. And in the another, we consider the energy associated with the p Laplacian, and plus infinity if these integrals are not finite. And the idea is to characterize what is what operator is the subdifferential of this, what is the gradient flow associated with this energy. But you do the following, you can write this Fn in this form. You take here the same, and here we have the characteristic function of Ax in y plus the characteristic function Iy in x over 2, and the same here. But if you define this kernel, Ka equal to the sum of this and Kb the sum of this, you can write associated with this kernel, you define one kind of one Laplacian energy, but here you take the kernel that so that you are only working in the partition respect to A, and in P you take the P Laplacian and this kernel. Okay, then we have that our energy functional that you want to study is the sum of these two. Then the idea is again to prove if the subdifferential of the sum is the sum of the subdifferential. But this, let me first say something about what is the subdifferential of these two different energy functionals. The first one we define. You have B, the partition B of the support of the measure of the probability, and then we define this MPB by the formula. This is the divergent M, but here we take the kernel given by this, and we prove that if we take the subdifferential respect to L2 now is fixed, the invariant measure is fixed. You take the subdifferential, then we have the Laplacian is equal to this, like in the classical case, in the case without weight. The same with the one Laplacian. The same. We say we prove that this is equal, is only belong to the subdifferential. But here also we give what is the subdifferential? What is the one Laplacian respect to the partition A? And we prove that again there is a function, bounded function, such that represents in some sense the gradient of u over the gradient of or the modulo of gradient of u. But here appear the kernel, and this. Now we need to multiply by the kernel in order. This sine function is the multivalued sine function. Is -1, 1, and -1, 1 as set. Okay. And assuming again the same assumption, we prove that the subdifferential of the sum is the sum of the subdifferential, and also the operator is incompletely negative. Again, applying the imaginary of maximal monotone operator in Hilbert space, we have this problem equal pose, and also we have the comparison principle and the contraction principle. Okay. I don't know my time. No, I have a lot. Maybe I'm going very muy rápido. Okay. Sorry. Example. Suppose we are in the first example. In the first example, the random wall is given by kernel in Rn, and then we consider two kernel integral equal to 1, and as consequence of a general result, we obtain the result that I don't know. I think is not known. You have here this non-local operator respect to one Laplacian respect to this kernel and the P Laplacian respect to the other kernel, and this problem have a uni-strong solution. Okay. Sorry. This is, now the same. Sorry. Respect to 1, respect to P. Okay, it's the same. Now, to finish, let me give you very simple example in very simple graph to see what is the difference between the when you make the sum of the energy and you take only one energy. The example is very simple because then we can obtain explicit solution. Okay. The first is the following. We take this very simple graph, 1, 2, 3, and then here the weight, A and B. This is the invariant measure. The probability is given by this. You move from here to here, and here you need to make the media, this media, and so on. This is the random walk. Then we consider the same random walk, but we consider the 1 Laplacian plus the 2 Laplacian, the Laplacian, okay, with some initial data. Then, if I call the function is function of only the 3 points, 1, 2, 3, I call xt equal u1t, yt in the point 2, and zt in the point 3. Then this equation, you can rewrite this equation like this system of ODE. But this system of ODE, you can see, is not a normal system because this function gt is undetermined. It's determined by the solution. But since we have uniqueness of the solution, we can solve this. We can solve until one time, and then have some behavior, and then another time, and finally we arrive to the media. Let me see. I take, this is in general, I fix, for instance, case A, the weight equal to 1, and then we see that the behavior depends strongly on the weight and also depends strongly on the initial data. Then this is the until one time T1, this is the solution of the ODE, or the solution of the problem. Here we have yt equal to zt given by this, and this is the firm. This is the time T1. Then appear another time, T2, such that we arrive in, in T1, we arrive, in this case, in T1, we arrive to the media. The media of the initial data is 1/4. And then after this time, you have the solution is constant equal 1/4. Okay, this is the media initial data. This is the solution. This is X, this is Y and Z, and right here, and then is constant equal to. This is the behavior in this simple case. But suppose, let me see. Suppose it's very easy to prove what happens if you separate the 1 Laplacian and the Laplacian. In the case of the Laplacian, the solution is given by this. Then right to the media, but in infinite time. You take the 1 Laplacian, the solution is given by this. You arrive in infinite time, you arrive to the media. And then, if you remember, here is something in between. Okay? And what happens if we change, and now we take the same weight, but we put more mass in the initial data, equal to, the other was equal to 1, here we put 10. You put 10, you have also until 1 time T1 given by this is the solution. But here there are, until this time, we have 3 different solutions, 3 different for 1, for 2, and for 3. But here, these solutions are equal. Then appear another time, the solution, this time T2, between T1 and T2, the solution now is given by this. Okay. And finally, we arrive also to the media in finite time. But the general results say. And what happened if we change now the initial data is equal to 1, but we put different weight. In the between 1 and 2, you put 10, and 2 and 3 put 1. This is the system. Also appear 1 time T1 given by this horrible number, such that this is equal to this. This is, in this case, the solution. And then, in this case, the x and y arrive to some point that are equal, but this is different, and continuous, and finally, in finite time, we arrive again to the media. Okay. And now, what about the second problem? In the second problem, we consider, for instance, this graph. It's 1, 2, 3, 4, and then we have put different weight A, B, C. Okay. And now we consider in 1, 2, and 3, 4, in 1, 2, and 3, 4, we consider the diffusion is the Laplacian, and in the another, no, is, I take, sorry. I consider, no, sorry. The Laplacian in 1, 2, 3, 4. 1, no, sorry. 1, 2, 3, 4, here the Laplacian, and here the 1 Laplacian. Okay? And this is the partition in order to have the 1 Laplacian in this edge and the Laplacian in the another. This is the partition. Then, again, for commodity, I call xt the solution in 1 and time t, yt, zt, and wt. And we want to solve what is the solution of this problem. The solution is given again by this ODE, but again, this function is indeterminate, belong to this multivalue sign, and this function belongs to the multivalue sign of D. And then you need to play with time in order to know what is this function. Again, we obtain a solution, but we have unique solution, and then permit to say that this is the good solution. Okay. This is the initial, put this initial data in 1, put 2, 0, 1, 2. This is correspond to this respect to the ODE, and this is the solution. Until 1 time T1, we have, this is X, Y. These are right here again to some common point, and then obtain another time T2, and then the solution now is this. Then these are right to this, but this is, the same. And finally, until T2, this is the solution. I write to the media, but in this case, I write to the media like in the Laplacian, in infinite time. Okay. And now I change, suppose in the another example, if we take C equal to 0, this is the graph. And for this graph, the solution, the situation is totally different. Also here we consider the Laplacian here and the 1 Laplacian here. Okay. This is the system of ODE you need to solve, again with these two determinate functions. You will consider, for instance, that the weight are equal to 1. So yes, C is we consider the characteristic the initial data here equal to 1, 1, 0, 0. And then the solution now is given by this. It's similar to the first case, but if you change the initial data, then the solution is totally different. You see, you have finally we are right to we are right to the media. And this is here in this paper that was accepted the past week in Mathematician Allen, and thanks for your attention.
Okay. We thank Mazon for this interesting lecture. Are there questions, remarks, complaints?
No, don't worry, I'm going to smoke. If there are no questions, I go to smoke, don't worry.
I mean, maybe I have some question. Do you know, I mean, you are dealing with these functionals in this very abstract setting, right? I mean, can you allow for coefficients or more delicate structures or more richer structures? Or
you mean in the differential operator?
Yeah, in the differential operator. Or
so also,
for U dependence.
We studied the P Laplacian. Really, we study. It's a very long paper. We study Lerelion. Lerelion with coefficient.
With coefficients.
And
also depending on U, on the solution, or just on the
depending on X.
Only on X. And do you have
for the moment? Yeah, depending only on X.
And on U, you do not have.
No, U
because it's different then.
It's more difficult, I think.
So, yeah. Okay. Are there further questions, remarks? So this is apparently not the case. We thank again Mazon.